bird mimicking flyers. So we can say that the ornithopters. So today I'm gonna show you guys about the interesting movie clips and our development and the simulation or control works using the ornithopters. So the first part is the flapping lives and robotic avian flyers I will introduce. This is the same as the previous lecture. The insect actually is very similar to the helicopter, just the multicopter. This is VTOL, so the vertical vertical takeoff and landing aircraft. But the bird is very similar to the fixed wing UAV. So it has the minimum speed, and then it has to go forward. So very similar to the bird. Bird cannot stay in the air in a certain position. But we are very interested in using this kind of the bird mimicking flyers for the monitoring of the scene or reconnaissance, because it has the benefits for energy saving, and then it can easily use the wind. So they are repeating flap and stopping and flapping and stopping, so they can be very adaptive to the wind. So we are very interested in that kind of things. So today I'm going to talk about the bird mimicking flyers in terms of the engineering technology. So actually the 1419, the Leonardo da Vinci, the plans for an ornithopter, as you can see here, and then after that there are many attempts by humans for flapping wings, but nowadays the German company, the faster, they are developing the articulated, the smart bird. So this is very surprising technology. And then it can stop the flapping, so it can glide, and then it is moving the head for directional control. So moving the head like this, and then the listening, they are developing the small bird mimicking flyers. They can fly indoors. So the wing shape is very similar to the pigeon. So it can fly successfully indoors. So our group is very motivated by this company, this German company. You can see the torsional motion and bending motion of the wings. The wing is very flexible. So that is very similar to the bird. And then it can glide and then flapping again. So you can save the energy. So bird can use the energy transfer between kinetic energy and potential energy. And then they are doing some swarm flight indoors. And then they are using some tracking technology by using the ultra wideband. So this is very high technology, actually. So motivated by this kind of research by the German company, Faster. So we are thinking there are increasing need for the development of biomimetic flyers. So actually there was question in the previous my lecture, well, why the flapper has some merits. So they can have the camouflage benefits that mimic birds and insects, and then they can have short takeoff and landing and low stall speed, low minimum speed, and then it has some excellent maneuverability, mobility, and low noise compared to the motor and propeller. So our team, since 2015, we have been doing modeling, control, and experiments and simulation with RC toys. So we have some toys in the commercial market. And then since 2017, we have been developing articulated Onisote design. So this shows our US CNU GULL, G-U-L-L. And then this is the RC flapping aircraft. This is some Korean company, but now the company is closed, bankrupt. Okay. So now let's move on to the system identification and control of the RC commercial Onisotes. So the currently Onisotes continuously moves the wing, generate and thrust. So it can have some complex form of a periodic movement, and then it has some span-wide twisting. That is very complicated motions. And then avian flyers, has more freedom in tail wings than fixed wing aircraft. I will show you later here. Can you see the tail of the RC Ornithopters? And then the good things is we have some manually controlled RC prototypes and toys. They are available now. So there are a few the research aircraft here, Smart Bird and Bionic Bird and Falcon. So the size is between 1 and 2 meters, but we selected the Magic Bird here. So wingspan is 1 meter, and then fuselage length is the 60 centimeters approximately, and weight is under 300. So our research goal is platform configuration and modification of the RC aircraft, and then modeling in terms of linear system, and then controller design and validation. But important thing is we don't have the exact nonlinear modeling. So firstly, we did flight experiment, and we gathered the data, flight data, and then reversely, we investigated the A and C matrices from the flight data. They can be viewed as the system identification, parameter estimation. So this is the Magic Bird commercial RC aircraft. So endurance is just 10 minutes, and flapping frequency we can control the 1 to 10 hertz. And then elevator and rudder deflections can be limited to this band. And then we installed the avionics board here. You guys know the Pixel Mini. This is very small sized Pixel series for computer. So just 15 gram. So we applied this Pixel Mini to the board mimicking RC aircraft. And then for system identification, we need input, software design. So we could apply step or doublet here, and then 3211 signal for the sufficient excitation to the dynamics. So flight, we have to excite the dynamic response by using the control surface. So up and down, so we can excite all range of the frequencies. So we implemented the software in flight code in autopilot environment. So we modified the PWM signal to additional channels. So we applied 3211, 3 up and 2 down, and 1 up, 1 down. So that means the time. So for 3 seconds up and 2 seconds down, so we can control the elevator for excitation. So this is the result. So actually we need angle of attack and side slip angle. So that is the relation to the wind. So we need alpha and beta, that is the angle of attack and side slip angle for aircraft. So that is difficult to get from the sensors inside the small aircraft. We need some angle of attack and beta vanes that is like this, but it is difficult to get the sensor mounted in the small aircraft. So we reversely computed these values from the other sensors with these equations. There is a very well-known equation UVW, that is in the Earth's fixed frame, and U1B1W1 is the frame, and UVW is body fixed frame velocity. So we can convert using the oil angle. So in this process, we can get UVW and BT total velocity. So finally, we can get the beta side slip angle. That is the relative angle side wind, and then alpha is the relative angle to the longitudinal vertical velocity. So you can see the noise from the flapping motion, because this is the real flapping, the flight data. So we apply the system identification technique for longitudinal and lateral directional system identification. So we need to estimate the parameters in the linear system here, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then plus 11. So we have 21 unknowns in the linear system here. Not at 21, because we have 3 unknowns here and 3 unknowns there. So 27 unknowns for A and B matrices. So we can run some optimization technique by using precondition conjugate for reversely getting the A and B matrix for linear system. So here the x hat, x true is the flight data, and x hat is the integrated computed state response from this system parameterized response. So from the flight data, we can get this kind of 27 unknowns. So here is the result of the system ID. This is the vertical and this is the lateral channel. So the blue line is the flight data. And then the dotted line is the model predicted from the system identification. So this is the result. So as you can see here, most of all the unknowns are found from the system identification process. So we can get the vertical A and B matrices and lateral A and B matrices. And then this is the eigenvalues of each channel. So as you can see here, there are two pairs of the stable eigenvalues, complex poles. And then in the lateral channel, we have the one stable eigenvalue and one stable real eigenvalue and one unstable eigenvalue. So this is the lower mode. So actually, in the lateral directional channel, we found one unstable poles. And then before flight test, we designed the controller using the PID and the feed forward terms here. So we decided the gains for linear system, and then this is actuator model and aircraft dynamics. So we applied the system ID result to this controller design and simulation. This is very simple linear simulation, actually. So as you can see here, the setter stem response is well tracked, and then the up and down motion is also well tracked. So this is the setter reference and comment. And then we check the altitude channel. So we apply the 30-meter comment to altitude change here, and the dotted line is the response of the dynamics. So as you can see here, the pitch is up. Yeah, pitch is going up and then go forward, go up to the 30-meter altitude increase. Yeah, finally we did flight experiment in this wind condition, and then altitude command is 30-meter up to the ground altitude, and then we designated 4 waypoint, and then after takeoff and altitude keeping, after that we activated waypoint tracking mode. This is stick auto fly. So actually the commercial RC flapper is very stable. So we are checking, we check the attitude control mode by using the stick command. So the pitch command and roll command is generated from the stick, from the RC controller, but the inside inner loop, the automatic control is working. And then after that, we activated waypoint tracking. This is automatic mode. Actually, one of our students lose the focus. so you cannot see properly. So this is the data. So this is the pitch angle, and this is roll angle. As you can see here, to track the 4 waypoint, the roll command is generated from the guidance channel. And then this is the altitude, and then this is throttle command. And then here, the onus of the takeoff from here and goes to the like this way, and then first waypoint, and then second waypoint, and then third waypoint, and fourth waypoint. So the waypoint tracking is successfully done by using the flapping wing, the bird mimicking flyer. So we can realize this kind of the aircraft can be used for waypoint tracking, and then the reconnaissance mission, and then it can fly with the small energy. Now let's move on to some interesting part. So now we are developing articulated bird mimicking flapping wing MAB. So like this way, can you see? Same, this is elbow. So not the straight wing. We are interested in the articulated wing. So it has some joint here. So it has some benefit. So in this figure, there is elbow, wrist, and shoulder here. So not the straight. This is elbow, the articulated. So the downstroke, it is stretched for full getting ripped, but the upstroke, we have to minimize the size to minimize the drag force from the wind. So like this way. So our research objective is articulated Unimstar design through mechanical formulas and verification of design, MATLAB, SolidWorks, and ADAMS tools. And then we developed articulated Unimstar aircraft. So, and then we performed initial flight experiment and verification. We are much motivated by the fact this size is 1 meter and wingspan is 2 meters. So this is very big. One is the smaller than this guy. And then analyze the kinematics via MATLAB and ADAMS. This is the inner wing formula. So we struggled to design the mechanical, the 4-bar link here. So derivation of the mechanical relation, but this is for the design of the inner wing using 4-bar. And then outer wing, we aimed to develop we applied this kind of the bar mechanism and gears. And then we verified our kinematics design via MATLAB and Adams. As you can see here, the green area means the downstroke, and then area means the upstroke. So according to our design, the MATLAB and Adams both verified our design is correct. So this is the ratio for actuating the flapping here from the shoulder. So, and our motor spec is as follows. And then our aimed flapping frequency is 3 Hz. And then this is here the actuator for flapping here, and then there is one motor. As you can see here, the tail freedom, degree of freedom is more than the fixed wings. And then we use the bearings here and there to make the intentional torsional motion on the wing. And then we use the commercial RC parts and receivers. Yeah, this is finally developed the US GUR, this unmanned system GUR. This is board name. So weight is 430 grams and span is 1.7 meter. So this is our design. So rear mechanism is very similar to the 3D model, verified our design. And then with application wing twisting test. So we applied some IR markers here and then we captured the motion of the wings using the motion capture camera here. And then this is board mechanism, and we collect the data from here in our PC. And then this is the thrust. So by using some force sensor here, so it is diving, but we wanna measure thrust generating from the flapping motion. So depending on the frequency, we can get with 70% throttle, we could get the thrust 440 grams. So this red area, so our normal operation range. Yeah, this is the test for forward ply. So we are measuring the thrust and the motion of the main wing. I will show you the bending and torsional motion using the slow motion. Can you see some bending and torsion? So the outer wing will experience more torsional motions. So just like bird. And then we could minimize the drag on during the upstroke. And then one of our students did an interesting experiment in the basketball playground. I will show you. Yeah, this is the world first flapping car. So we verified it has the forward force, the thrust in the forward direction on the ground. And then now finally at last we did the initial flight in Cheongju near Daejeon. Yeah, this is under our expectation. And then yes, so we failed in the initial phase because it has insufficient thrust and weight. So we changed the throttle mechanism, and then we realized some center of gravity problem. I will show you. This is the flight experiment in our university. Yeah. So we struggled from the flight testing, many fails and many failures. So our research team was very disappointed in this kind of the flight experiment failures. So this is the last year's flight in our. Yeah, it's finally our ornithopter is in the air.
원래 저랬나? 뭔가 좀 이상한데?
So we modified the flapping mechanism and the wing shape and then position of the center of gravity. So we successfully make this in the air last year. So we are modifying mechanism, and so this is ongoing work. So our students is laughing.
Stonea.
So actually this kind of the bird mimicking flyer, if they are going up, so we cannot discriminate it from the bird. So actually it has some camouflage effect. And then the speed of them are very similar to the bird, and then flapping motion make the enemy is confused from their radar system. Okay, now I will finalize my presentation with discussions and Q&A. So we did system identification and controller design and simulations of RC ornithopters. And then system ID were done successfully with a modified open source autopilot environment, specifically autopilot. I've not used the PX4, so we applied the autopilot. And then altitude, port, and waypoint navigation were successfully performed. So I think this showed that bio-inspired ornithopters can be applied to similar mission with fixed-wing UAVs with the high camouflage effect. And then we developed an articulated ornithopter, CNU Girl. The flapping kinematics was mechanically designed and developed and verified. And then we did various ground tests, and then we failed many times. So with the trial and error, so initial flight tests were successfully performed in last year. So we have been doing ongoing effort to mimic bird. So we are developing small-sized articulated CNU Girl Mini. And then I have an ambition to do research about flap and gliding using wind information. So, so I want to stop the flapping motion in the air and then glide and then using the wind and soaring again. So we can maximize the flight time, this kind of technology. So I'm aiming to go forward for this kind of direction. Thanks for your attention. And do you have any questions? So, Dr.
Okay.
Suchan, yeah.
Thank you very much, Prof. Kim. Very, very interesting, Prof. Kim. I think Mr. Hendro will make a competition, basketball competition using bird mimicking soon, maybe. It's because in Germany, the Festoli, they have a very, very good birds mimicking. Yeah, it's very, very interesting. Yeah. Anyway, we will have a question and answer at the end.
Yep.
We have Dr. Hendro presentation. Before he gave presentation, I will briefly read his educational background. Actually, it's in Indonesia. He did his doctoral from Mechanical Engineering, National Taiwan University of Science and Technology, Taipei, Taiwan. And he is now a CEO of Central of Excellence for Mechatronic and Industrial Automation. As far as I know, till now, we don't have mimicking of flyers. I don't know, soon after having inspired by Prof. Kim, maybe he will do some mimicking of flyers. Okay, Dr. Hendro, time is yours, Dr. Hendro.
Okay, thank you, Pak Subhan, and excellent presentation from Professor Kim. Good morning, everybody. Different than Professor Kim's presentations today. So this time presentations, we would like to emphasize on how to initiate. So let us introduce the initiation. The initiation, designing and developing a collaborative robot machine instead of differentiation of industrial robotics. So I will try to put the presentation to the share screen. Okay, this one. Oh, which one is this? Oh, this one. Sorry. Okay. Is my PPT already available on the screen?
Yes,
Okay.
very clear.
Thank you. Today's presentation probably will not take a long time. Probably will take a short time since that parallelly in our laboratory, since I'm in the office at home, office but at home, since that the pandemic is still happening in our region, in robotics area at ITS, our students are there to provide and to prepare the demonstration that will be performed by mathematics students, Pak Subhan, who doing internship in our laboratory, and we are supported by PT Handal Yasindo Sejahtera, one industry in Indonesia, who primarily authorized by Universal Robots to distribute the products of collaborative robots of Universal Robots. So at the end of the presentation, I would like to ask the permission of the committee, Pak Subhan and colleagues from Mathematics Department, to let one account of our student, Slatis actually, to uh, to pin the account that everybody can see the real live demonstration how to operate the collaborative robots. So it is new actually for us in robotics in Indonesia actually also, probably different in Korea. So apologize Professor Kim that I will try to introduce some introduction only. It's different kind than advanced presentation of yours. So just let's start our presentations. Okay, uh, a robot, as we know, uh, there are many kind of robots that already developed in daily applications. Principally, there are two kinds of manipulators that we call it robot, a serial manipulator and also parallel manipulator. And many times that as we can find easily at the industry or in laboratories, usually we find robots as a serial manipulators. But uh, in recent days, people or eventually ours, us at the robotics ITS, we develop different kinds of types of robots, such as humanoid robots, also aerial robots, but not so advanced as Professor Kim. So he inspired us to develop a new division for our competition for the next competition with the flapping robots. Since that there are only institutions, two universities in Indonesia already developed these flapping robots, Pak Subhan. The first university is University of Gajah Mada. Since last year, they already developed this kind of flapping robots, and this year they are also trying to performing articulated flapping robots at UGM, and the second is University of 11 Maret in Surakarta or Solo. Okay, in definition of robots, uh, we know that robot is a tool. Robot is a helping media for human being to uh, perform the jobs, daily jobs in a daily activity of a human being. What interesting is recently, since 2000s somethings, it is developed so-called that a collaborative robots. What is a collaborative robots? In 2005, Universal Robots already established and developed the first generation of the collaborative robots. Omron, one of the biggest company who uh, intensively develop many application of mechanical and also electrical application together, mechatronics application. They define cobots as a collaborative robots that can be used to build an innovative and intelligent manufacturing environment where humans and machines work in harmony. That is the key point actually. Humans and machines work in harmony. In other words, in Wikipedia, we found that cobots or collaborative robots are robots intended for direct human-robot interaction within a shared space or where humans and robots are in close proximity, as cobots are intended to work alongside humans. So what is different? The classical robots in industrial application compare to the collaborative robots, which is actually also part of industrial robots. If we talk about the collaborative robots, so we have to pay attention on how the safety, how the comfortability of a human being in performing their activity or their daily jobs. That's why in several standardization of safety and also security and also environmental friendly regulation. Collaborative robots is regulated by such several standards. As we can see that collaborative robots means that a robot can collaborate with a human. It is a different story to the industrial classical robots that we can find easily in industrial application, that they have a spirit environment than the human being environment. They intended to be separated since that they work very intense. The danger of how they work is also high risk to the human being. But nowadays, we try to blend it, to blend them together, to cooperate them together between a human being and also the robots, to cooperate together, to collaborate together. So that's why some regulations we need to pay attention on it, that a such of collaborative robots supposed to be completed, supposed to be installed with some sensors, especially some torque force sensors, so they may identify whether they uh, hit or they will be interrupted some intervention of by the human being to the robots. As we can see also at the presentation, that it is not easy to develop some robots to hold an egg. It is also not easy to develop some robots to peel the banana skins. And also it is not easy to collaborate it between two arms of independent or standalone arms of robots. So in this phase, in our center, we are trying now to start to designing and to developing the collaborative robots. Uh, in the phase of designing, we try to get some reference by the Universal Robot Collaborative Robots and also some others references such as an Omron and also a different kind of type of collaborative robots from different companies. But the key point of designing here that we refers to several commercialized products. The key point that we want to get from the designing phase by observing of the commercial product is to get the design criteria. Since that several industry or several robots are already developed, they are designed with the several conditions, with the several payloads, with several force in range of 3 kilograms, 5 kilograms, 10 kilograms, 16 kilograms. Compared to the industrial robots that usually they may accommodate the force of such 1 ton or several tonnage of the payload of the robots. There are the biggest difference between the industrial classical robots in industry without the sensings of the human being interventions to the collaborative robots that intentionally they are designed, they are dedicated to collaborate with the human being. So we are currently just starting now to design the design criteria actually focusedly in our center. And the developing phase also parallelly with the several students from mechanical industry engineering department and also physics department, mathematics department, of course, and mostly the current students who perform internship in our center from mathematics department. Developing its the phase how actually to get the configuration of the sensings configuration of collaborative robots, uh, how sensitive is the collaborative robots, and how accurate that robots can move, can perform the trajectory or waypoint that already designed by the technician or the engineer. Okay. Uh, we refers to three kinds of the commercials or ready developed robots. The first is collaborative robots by the universal robots. Uh, and nowadays in our laboratory, there is one collaborative robots provided by our industry partner, PT Handal Yasindo Sejahtera. They support us by supplying us one collaborative robots with type of UR5, but without E specifications. E means that the collaborative robots by the UR already completed with the sensing devices that we may collect all information, identify the information such as the force, torque, and also velocity simultaneously. But the robot in the previous version in CB type, they still don't have this kind of specification, or they are not supported yet. And also Omron. So we can see that although a different company, they try to develop collaborative robots, but the outlook, the designs, it looks like all similar. So collaborative robots that try to develop by several developers by industries, they have identically geometrical shapes and also configurations. The cobots configurations consists of 6 degree of freedoms, and normally they consist of 3 main components. The first components are the robot itself. The second component is the panel or the control panel. And the third is the programming pendant or the remote control, remotely or, or wirely. As we know that robotics, we cannot separate it with maths or with formulation. So uh, what we have to perform, how to how to identify that our robots has uh, such a certain performance that we would like to have. We need to analyze the robots by dynamics analysis and also kinematics analysis. As we can see, there is not only one thing that we need to complete to design the robots, such as mathematics contribution, mechanics contribution, electric contribution, and also software contribution. All are integrated in how the way to develop the robots. Okay, so what is actually maths in cobots? Uh, Robots, we also have one speaker here. It is Dr. Latifah. She is my colleague in mechanical engineering department, and she also expertise in robotics mechanism. And this formula looks very, very uh, uh, close to Bu Latifah. So math in cobots relatively close to rotational matrix and also transformation matrix. There is some illustration in our presentation that we have to perform to design the performance criteria of our robots using a rotational matrix and also transformation matrix by homogeneous matrix or non-holonomic robot performance matrix or such different type of robots. And in robotics, Jacobian matrix, one of tools that we can use, help to know the relation between joint velocities and effective velocities at the robots. There are many tools of maths that we may apply to identify and also to design the performance criteria, how to move our robots. There is one example in MATLAB, the simulation in MATLAB, how to calculate the rotational transformation matrix using a Jacobian matrix. As we see here, we may design the forward motions, and we will identify the inverse information of our robot performance, and vice versa. We may put the information related to the inverse kinematics information, and we will get the abscissa coordinate informations. Okay. And now we are computing now with PT Handal Yasindo Sejahtera at Robotics Center. As you can see, the first collaborating ourselves first. It is time for us now to go outside to ask everybody to join with us and doing reverse engineering starting from the end and will be finished at the beginning. It is a philosophy of reverse engineering, and we will focus on high-level control design in developing of a collaborative robot, since that many industry already developed this kind of collaborative robots, and starting to our own high-level control collaborative robots, and stay be happy, since that happiness may increase our immunity. And as I mentioned at the beginning of the presentation, uh, Pak Subhan, I would like to ask your permission to access our laboratory to show you the live demonstration will be performed by our students, especially med students who already prepare. So please.
Who is his name, Mr. Hendro?
Slatis, actually. Slatis Zoom's accounts is a Slatis account.
Just a second.
Wait. Slatis?
Just a second. I have to make us a co-host first. ITS.
Okay.
Ditulis apa, Mr. Oh yeah, okay, it's fine. I got it.
Okay. I don't know what kind of name that they use to sign into our
ITS
Zoom.
ITS Latis. Okay.
That one. Yes, ITS Latifah Rashmi.
So now thank you. She is co-host now.
She is co-host now. Okay. Okay. Thank you, Pak Subhan, for the opportunity. So, Slatis, please show your demonstrations from our labs. Slatis or Sulastri or Salma? Okay.
I'm sorry, Mr. Hendro. Set your share screen.
Okay. Already. So there is robots from Handal Yasindo Sejahtera. They support us. They supply us these robots, and we will explore this performance of robots for the beginning phase by mathematics students, how to identify actually the performance of the robots. So they will try to perform some transformations, matrix identification using the Jacobian or Hamiltonian approach. And as you can see, this robot can move automatically by itself, but this time this robot is operated by mathematics students. It's not mechanical students, it's not electric department students, but math students, and even a female mathematics student. So sorry, Professor Kim, we just starting our fun at Robotics Center. We would like to ask everybody to get have fun together, especially Bu Latifah. Her expertise is also in this field. So in this opportunity, I also would like to invite her to come back to Robotics Center with us to get this fun together. So Slatis, some of you may say something or explain something.
Yes, this is Robert from PT Handal and we can control the robot from the touch pendant.
Okay, can you show your touch pendant also with
Yes.
one of you who hold the pendant to show all the audience, all the viewers that you operate the robots? Okay,
This is
and where are you?
the touch pendant of robot. We can dengan
We can operate the robot manual or
So who is this? Sulastri or Slati or Salma or Mega or
automation. Here. So we can
it seems that
sorry, Pak.
oh Cory. Okay, Cory is master students from mathematics also.
Master Hendro is hijacking my student actually.
Thank you for supplying the students to our center, Pak Subhan.
Yeah, it's
Okay.
quite good collaboration.
Yes.
So happen Prof Kim in Indonesia is interdepartment. We have collaborate interdepartment, especially with the Center of Mechatronic and Automation.
Okay, I think that's all of our presentation from today. Thank you, Pak Subhan.
Okay, okay. Thank you very much, Mr. Hendro and his team. Yeah, hope we can have more collaboration in the future, Mr. Hendro. Okay. Now the next presenter is Dr. Enda Rahmati. She is from Mathematics Department, from Laboratory of Mathematics for Industry and Finance Laboratory. She graduated for bachelor and master from ITS, and her doctoral graduated from Financial Mathematics Wenda from Wollongong University, Australia. Wenda, time is yours. Please.
Okay, thank you Pak Subhan for the introduction. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning everyone, and good morning to Pak Hendro too.
Good
Pak
morning,
Hendro
Bu
and
Enda.
Professor Kim has. Good morning, Pak. Yeah. Both of them have amazing presentation, and I think the next presenter, Dr. Latifah, actually she's my little sister actually. She is awesome also, I think. And I think I have a different topic and from other presenters. They have all about robotics, and I would like in this opportunity, I would like to present about still my current research about COVID-19 modeling. So my presentation is about COVID modeling and its extension in terms of financial mathematics. Here I would like to have the outline of my presentation. We have in mathematics department, we have a study group, research group about COVID modeling, and we have done 3 methods to predict the spread of the COVID-19. So we have 3 methods here. It is a hybrid method between the physical epidemic model cooperated with the artificial intelligence or machine learning. And we have quite a big and excellent research team member in this for this topic. And here, the extension about the COVID-19 modeling, we have cooperation also with the researchers from other university. It is SimCOVIDs, and we have about the topic about reproduction number of COVID-19 spread. And also currently we are working, especially with my student, for the topic in financial math relating to COVID-19 modeling. So I would like to start my talk. So why is mathematics used for modeling? Actually, here, the step of prediction model and evaluation. Here, we have the prediction model as an input for formulation, implementation, and policy evaluation. So that is the function of prediction model, and we use the mathematics to obtain the prediction model. And after the policy implementation, they can give feedback to improve our mathematical prediction model. So that is why the mathematics modeling is like a continuous improvement process in order to get better and better modeling to present the phenomena. And this is the model that we use. It is called compartment model, and we use a SIRD model. Actually, there are a lot of model, and it is there are many complicated model, but in this research, we use just a simple model that can represent and can be incorporated with the existing data of COVID-19 in Indonesia and most of the countries. So here we have classes of population. It is called susceptible, infected, recovered, and death. Susceptible means that this is the class of individual who has high risk of contracting with COVID-19. And the infected class is the class of individual who is already infected by the COVID-19. And the recovered is the population or individual who has recovered from COVID-19, and it is assumed not to get sick anymore. So that is the assumption that we use in this model. And also the infected individual can also die because of the virus. So this is the SIRD differential equation. It is the ordinary differential equation. There are some constant and also initial parameter values that need to be estimated. So here we use three types of method to estimate the initial parameter values and also the constants in order to get the prediction of the COVID-19 spread. And this is the assumption. The assumption is it is isolated from other region. So the spread is only for one region, and individuals in the same class have same characteristic, and their movement can be described. And also total population is assumed to be constant, and birth rate and death rate are the same. And this is the explanation about variables and the constant. And here the first hybrid model that we use is a genetic algorithm SIRD model. So in this model, our method, we estimate the parameters and also the initial values of COVID-19 spread by using genetic algorithm. So this is actually a genetic algorithm is an algorithm that mimics a natural evolutionary model by using genetic inheritance. And genetic algorithm uses a crossover and mutation operator to process the chromosome in the population until we get the best result of prediction. This is the genetic algorithm workflow. Starting from generate initial population and then calculate the value of fitness function, and then we select the best fitted fitness function, and then it is like a closed loop that that will stop after satisfying the stopping criterion. The stopping criterion is related to the best prediction or the smallest the percentage of error. And here the detailed stage of the genetic algorithm. Here we have the daily data of infected, recovered, and also death. And the data we try to apply to Indonesian data, and we obtain the data from the official website of the government. So we assume that the data is representing the condition of the COVID-19 spread. And there are 5 stages, and the basic point of these stages is to have the best chromosome. And in this step, we can guarantee that the new chromosome is definitely better or the same as the previous chromosome. So that is the basic algorithm. Here, the parameters found by the genetic algorithm based on Indonesia data from March 2nd to August 25th, 2020. And we use these optimal parameters for the GAEKF SRD model. And this is the result of the simulation. We can see that there are some, the distance between the actual data and the prediction result. So this is the result for genetic algorithm model. Now, the second method or model, we incorporate extended Kalman filter to the GASIRD. Here, the basic algorithm of extended Kalman filter, I will just go through it to save the time. And I would like to show this is the discrete model of the epidemic or SIRD differential equation, and we use this discrete model to apply in extended Kalman filter. So in extended Kalman filter, we can update the prediction based on the incoming actual data. So in that process, the result will be better because in one step ahead, the prediction will be improved by the incoming actual data. So this is the result of the simulation, and we can see that the prediction result can follow the actual data better than the GASIRD model. So here we can consider that AKF can improve the GASIRD model. And now the third model is different from the first two hybrid model. Here the model is purely a machine learning method. So this called ensemble support vector regression model. And this is the basic algorithm of the method. I will not, I'll go through it just at a glance. And this is the last formula using the method to be solved. And based on equation 5 and 6, we can provide the simulation result like this. And basically, the first step in ensemble SVR model is about ensemble or generating sample data, and it will ensemble the data, the actual data from other countries' data. So the idea here that we will find the most suitable or the most fitted distribution of other countries' data to Indonesian data. So here we use China, South Korea, and Malaysia to be our ensemble sample data. As by this plot, we can see that the red line, it is China, and then the yellow line is South Korea, and the blue is Malaysia. You can see that for each classes of individual confirmed infected, recovered, and also death, the closest distribution to Indonesian data is based on data from China, South Korea, and Malaysia. So here actually we did the determination of the distribution based on this visual graph. And for a better result, maybe the next we can also use some statistical testing method to determine which distribution is the most suitable to Indonesian data. So this is the result of the simulation of COVID-19 by using the ensemble SVR model. And we can see that for China, also Malaysia, the prediction result can fit it very good with the actual data. So the dot sign here, it is the actual data. So it can fit very well. So, and the result of the prediction by using the ensemble SVR model is outperformed than the other two previous model. So based on that, this result, we can conclude that ensemble SVR can provide the best prediction. So this is the COVID-19 modeling. As an extension, we can use the prediction of the spread of COVID-19 to determine other subject or other field. The first is about reproduction number. Reproduction number means that we can use reproduction number to measure how the COVID-19 severity of spread. So by having the reproduction number, we can measure whether the spread is weaker or still very strong in our surrounding. So in modeling the disease transmission, can help us to inform and evaluate control policies. So we can sometimes heard from the government about reproduction number and how it can be used to decide whether the this partial lockdown, like in Jakarta, will be continued or will be stopped based on the current calculation of the reproduction number. And this is the paper by the SynCovid team where we are joining their research. And here the formula based on the SIRD model. So the previous SIRD model that I have shown to all of you, we can extend the model to calculate the reproduction number. So we can obtain equation 7. And by augmenting the model, we can have the new discrete RD model. In this paper, the authors or the researcher also incorporate extended Kalman filter to the model, but in different way from the one that I have explained to you previously. And this is the equation, the discrete equation, and we use this for simulation. And this is the result of RT based on West Java province. So here we can see that the RT of the red line presenting the RT or the reproduction number. This is the data up to August 2020. And we can see the blue bars, they are the active cases. And we use the confidence interval for 95%. So we can see that after August, the RT is more than 1. Why 1, RT equal to 1 is used to be the guideline of this measure, because if we have the reproduction number is below 1, it means that the spread of COVID-19 will be weaker, and we can hope that the spread is not too strong anymore, and we can hope that the pandemic will be over as the reproduction number decreases. But we still have more than 1 here. And this is the simulation of the active cases and remove or death cases based on the method, and we can see that it is exactly, or it is excellent. It has excellent fit with the actual data. And the second extension is related to economic problem. As we know that during the COVID-19 pandemic, we have so many economic problems from the, what is it? We call it, the economic is slowing down, and then there are so many companies which suffer from bankruptcy because they cannot have their money or their cash flow running well. So there are so many economic problems relating to COVID-19 pandemic. In this case, I would like to present based on this paper by Toda, and it is actually our student in Department of Mathematics in Lab of Mathematics of Industry and Financial. And it uses the SIR model, which is simpler than our previous model, and we evaluate the economic impact to the stock or saham in Indonesian, in Bahasa. So here we try to evaluate based on this paper the potential economic impact by using a stylized production-based asset pricing model. It is because we have some extreme uncertainty and we have to make some economic decision during the pandemic. And this is the basic model of SIR that we use. And this is the equation, the differential equation for SIR, and it can be solved by using our first three methods of COVID-19 modeling, which are the hybrid model or the machine learning method. So basically, we need some methods, some other methods to solve this and to provide the prediction. Here, we need to predict the who are infected and who are recovered, because it is related to the employee of some companies. So the companies have stock, and the stock price will be definitely depend on the condition of the company, and the company condition depend on how the employee inside, how the condition of the employee, are they healthy or not, to be able to run the production process of the company. So it will have a big impact to determine the number of infected people or recovered people in this case. So here we assume that the economy consists of capitalists and workers, and they own the capital, stock, and labor. And here, the paper used the capital growth rate as exogenous and log normal distributed. And here the capitalists hire labor at competitive market and produce a perishable good. And here we will use Cobb-Douglas production function. So this is the type of utility function of the production process. And here, this is the information about the Cobb-Douglas production function. And this is the function that will be used for the study. However, it can be changed by using another production function. But suppose this type of production function. After that, we will try to measure the constant relative risk aversion. As we know that investor or the capitalists, they have natural behavior to be risk averse. Risk averse means that they don't like risk. They avoid risk. So that is the basic or the natural behavior of the capitalists that we have to consider in this modeling. So here we have this measure based on equation 18. So this is the equation that we use. C is the consumption, and this is the constant CRRA. And the asset pricing here, we calculate the firm profit based on the Cobb's production function. This is the Cobb-Douglas production function, which has which represent the profit that come to the company, because we have labor here, and also we have let me see the K. K is capital input. So here the capital input and the labor. So the labor can produce goods, product that can give the company profit. And the total or the net profit will be minus wage. Wage mean the what is it? The salary of the labor. So this is the profit. And to obtain the profit maximization, we have the first derivative of the function equal to 0. Then we can have this function. And by using equation 22, we assume that firm's profit should be equal to consumption. And this is the natural condition of the production and company. So we have this. And there is a stochastic discount factor. Here we use a discount factor because we try to value what happened in the future, but we will see the case from the current point of view. That's why it is called discounting factor. Okay, and this is the equation that we will use for calculating the price consumption ratio. And that is the last equation to obtain VT for having the impact of the COVID-19 to the economic in terms of the stock price of company. And the second topic of economic problem is about the operational risk management model for pandemics. The idea is that if a company has their employee infected by COVID-19, which maybe you ever heard about the Sampurna company who has to close their company for a while because around 100 employees got infected by COVID-19. And the idea here, how to measure or to maximize the profit of the firm by continuing to operate or suspend the business. So the idea is close the firm or still open the firm while they get their employee infected by COVID-19. And the second idea is, does a firm intention to maximize its value conflict with its desire to control the disease? As we know that in Sampurna case, there are some opinion that they have to close, but Sampurnas will suffer very great loss in that way if they close the company. However, they should also consider that if they open the company, they will have the disease will spread worse than before. So they have to juggling between the two important consideration. And the last is about the optimal triggers for firms to implement the reactivation strategy. So here there are two stages. The first stage that we adapt an epidemic model, which is a bit different from the ones that I already talked to you previously. And also the second stage is incorporating a regime switching. Regime switching means that we need to consider two state or two condition of the company. Should they open the company or should they close the company regarding to the COVID-19 spread? And this is the model, simpler model that we will try to apply. It is called SI, only susceptible and infected. And stochastic modified SI, allowing the external contagions and death. So the company can hire a new employees to replace their infected employees. And also the company will lose their employees due to the death caused by COVID-19. So this is the mathematical equation that we will use in the study. And this is the cash flow function in a regime switching model that is related to the COVID-19 model. And I think that's all for my presentation today. And I would like to thanks to Department of Mathematics of ITS and also the research group of SimCovid. And these are our reference. And thank you.
Okay, thank you very much, Bu Enda, for very good presentation and the COVID update. Yeah, hopefully later we have a discussion in the COVID as well, even though it's not robotic. Yeah. Anyway, now we have our speakers, Dr. Latifah Rashmi. She is from System Engineering and Control Laboratory. Department of Mechanical Engineering. Just a second, I read a little bit about her background. He graduated for her bachelor from Mechanical Engineering, Institut Teknologi 10 November Surabaya, and for master and doctoral, she graduated from École Centrale de Nantes, France. So her research interest is about design of mechanism, kinematics, dynamic, reconfigurable manipulator, parallel manipulator, cable-driven parallel robot, and type synthesis. And now she is the head of Laboratory of Control and System Engineering. Bu Latifah, time is yours. Monggo, Bu.
Terima kasih Pak Subhan. Good morning everybody. Welcome to today's talk. First of all, I'd like to deliver my gratitude to Pak Subhan for inviting me, and thank you for Department of Mathematics. Good morning, Professor Kim. Good morning, Pak Hendro. He's one of my teachers. And good morning also to Bu Enda. She's also my teacher when I was still even 12 years old.
Oh yeah?
And yeah, we are neighbors. Now we'll come back to robotics again. But the robotics that I will talk about is more about cable robots and parallel manipulators. I'm using one tool which is called as a algebraic geometry. Before coming to the main talk, please introduce, I am Latifah Rashmi. I'm from Department of Mechanical Engineering. Here is the front view of my department. You can see in the right picture. I'm from ITS. Okay. So you have seen the robot presented by Professor Hendro Nurhadi. So why algebraic geometry? Why using algebraic geometry in robotics? I'm bringing this challenge to answer. As we can see in the right picture, this robot is picking an object and placing it in another position. So before commanding this robot for doing this, we need to know first what is the motion that this robot can perform, or what is the trajectories, the path that this robot is able to trace, and what is the workspace actually, what is the maximum envelope can be reached by this robot. And the last thing is what I've been juggling for the past few years is singularities. So if you remember last month on October, there were 3 physicists won the Nobel Prize about black holes, but I'm not going to talk about black hole. I just want to say one common thing between black hole and robotics is singularities. So in robotics, we also face singularities, and I will show you why, what is singularities. So one simple illustrations. This is one illustration of so many illustrations of singularities. In the bottom picture, in the bottom animation, you see that the robot should maintain constant velocity, but at some point the robot collapses, the robot drops. So the robot is not able to maintain his or her behaviors for doing our desired task. So this is singularities. So for doing analysis in motion, singularities, trajectories, workspace, we are using algebraic geometry. So of course, for doing that, as you can see the previous presentations, very amazing presentations, we have to formulate a set of equations, polynomials of degree. Can be very high degree. It can be degree 10, degree 40, and etc. So how are we going to solve this set of equations? We need a powerful tool, and this tool I'm choosing is algebraic geometry. Now, what is algebraic geometry and what kind of tools that we are going to use? So in the first presentation, if you paid attention, in robotics, even in the second presentation, in robotics, we always deal with transformation. So we transform the position to the frame that we wanted. We call it as a fixed frame. This is a very simple illustrations. So for doing the transformations, we may choose many types of parametrizations. We can use Euler angles, U, V, W, pitch, roll, and yaw. But the drawbacks of using that is we face a gimbal lock. You probably are familiar with this. So in gimbal lock, if you rotate an airplane with 3 angles, at some point, these 3 rings in the animations, the pink, the green, and the yellow, they will be placed at the same position. So if you are facing this condition, any angle that you generate, you cannot get out from that position. So this gimbal lock is also singularities, but singularity in the parameters, not in the robot. So we don't use these parameters. Now we move on to the quaternions. So homogeneous, one reason we are using quaternions is because it is homogeneous. So we don't face gimbal lock in our parameters. Another tool we are using is primary decomposition. Basically, this is the same as what we have probably even in elementary school. So for example, if we have 20, we have to decompose it into prime numbers and so on. So we use these primary decompositions not for numbers, but for set of equations. And the second, the next tool we are using is Grobner basis. This is quite a new tool developed by Austrian geometricians, mathematicians for solving mostly the symbolic equations. And the fourth tools is vector and matrix operations. This is a very basic tool that we have to use to solve engineering problems. So by using all of these combinations, now we can solve a set of equations in the mechanisms. So the first one, before explaining about the results, I want to also introduce to you what is parallel manipulator and what is cable robots. Those two are my title. So the first one, here is the parallel manipulators. If you see in the right picture, we have a robot. This is also a robot. So robotics is very wide, it's very diverse. Robot is not only in the shape of human. So robot can be in any shapes. It can be in the shape of birds, in the shapes of animals, or even like this in the shape of a parallel manipulator, parallel mechanisms. So as you can see in the right picture, this is one example of parallel manipulators. It has what we call as a 3 legs. If you count, there are 3, like a 3 sticks. So we call it as a legs, like human legs. And the top part, it can move. So this motion, we used to use it for many applications in industry, even for surgery. So these mechanisms, if you replace the bottom part, the bottom joint with what we call as a universal joint, so we might have many types of motions. So we call here as a different mobility. Mobility is also a type of motions, different mobility, and we call it as a lockable joints. So in manipulators, if you are interested in working on manipulators, you will deal a lot with joints. So here, instead of using a simple pivot or pin, so we replace it with two pins, so it becomes a universal joint. So one joint can be locked, so we call it as a lockable joint. And by taking advantage of this lockable joint, we may reach many types of architecture inherently. So probably from outside, it is not clearly seen, but actually by rotating one of the joint discretely, we may reach different kind of architecture. So this robot is actually, this belongs to my partners, and we met in a conference. Then we have something in common. I have the tools and he has the problem with his robots, that his robot, he doesn't understand how this robot changed from one architecture to another architecture. So actually, before meeting my partner, separately, I have analyzed from fundamental point of view this kind of robot. So this robot in blue, we printed this mechanism. This mechanism is actually, at that time, we didn't know whether this robot is possible or not. So we just printed and analyzed this robot. So how did we use the algebraic geometry? So in the right picture, you can see that if we break down this robot and we take a look only one leg like this, like A1 and B1, so we can conclude that this point A1, it has only one axis S, and point B1, it can rotate about the axis S on the yellow plane. So this is basically geometry, like the way you imagine a pyramid, a circle, and a sphere. So this is the same. So we imagine that point B is rotating on the plane yellow. So from this geometry, we formulate its algebra. So that's why we call it algebraic geometry. This is very simple. The methodology is very simple, but it's very powerful. And then we can formulate the vector operations that the line A, B, they are always perpendicular to each other. So it means the dot product is a vector operations is equal to 0. So from these formulations, we found many results about these manipulators, that the workspace, so the workspace again is the space, the points in the three-dimensional space that can be reached by the moving platform. So the platform, it is moving. So the shape of the workspace, and for mathematicians, I believe you are all familiar with this. I knew this surface actually at the time when I found this. So I didn't know this surface before. So actually this mechanism is able to perform or to trace points just like the Steiner surface. And this actually this surface was already pointed out by mechanical engineers in 1990 in their book, but they didn't know that their theory can be realized in real life. And by the time when I analyzed these mechanisms, I printed these mechanisms, and I didn't know at that time, because I work a lot from fundamental point of view, I didn't know at the time that this mechanism can be realized and can be used and can be brought up for many applications. But then when I met my partners, so this mechanism is actually one part of his mechanism. So this is very, very interesting. So this is actually my partner's mechanisms, and the previous picture that I print is my mechanisms. So we combine our results. We did some we did some computations again, and if we change the angle, how does the robot move, and what kind of surface that the robot can trace, and so on. So actually we collaborate in this, and this is the robot. So he can perform, he work a lot with the robot, and he can perform the robot to move and so on, and also to trace the surface. And if we change the angle of the orientation, if you remember the joint, the angle P here, if we change the angle, so the surface volume will also change. So if we change from 30 degrees, 45 degrees, 60 degrees, and this one that I circle is actually my manipulators that I analyzed before. So we actually matched, and this is the power of collaborations, that we matched our expertises and we got even more results. Another parallel manipulator is what we call as a 4 degree of freedom. So in this 4 degree of freedom, now we have 4 legs. So if you count, there are 4, 1, 2, 3, and 4 in this picture. When analyzing these mechanisms, we faced many problems. The first one is higher degree polynomials. The equations, it has 40 degree polynomials. So from fundamental point of view, this might be interesting to have equations of very fascinating equations. But from application point of view, if those equations cannot be illustrated, then it is nothing. So this is a big problem. We faced a higher degree polynomials. We use primary decomposition, but then it didn't work because we have a very long equations. So the software didn't work, and it is computationally expensive, which means we need even more memories in the computer. So for our field, working in symbolic, if we use too many, we need more and memory of the computer. But actually we are working in the symbolic point of view, then we need to modify our equations. So usually that's the hint. So what we did, we decomposed these parallel mechanisms into 2. So you see in the right picture, we decompose it into 2, the right one and the left one. Then it is our computations. And again, what is the algebraic geometry that we derived here? Again, we take a look, what is the axis of the joint B and the joint C, how they are reacting to each other. Then we can formulate that lines. So in geometry, we work a lot with lines, which is very simple. I believe you all can do the same. So the line V, the line N, and the line connecting BC, they are all lying on the same plane, which is a yellow plane. So again, we can formulate its algebraic equations, and these are the equations for my manipulators. And finally, from this equation, some computations we did, and we came up with results that this parallel mechanisms is able to perform. Please excuse me that we are using more robotics terminology. So these mechanisms or this manipulator, this robot is able to perform 4 degree of freedom for types of motions, and it has 2 types of 4 degree of freedom motion. Type number 1, type number 2, and type number 3 is actually no longer 4 degree of freedom, but it is 2 degree of freedom. The drawbacks of this mechanism, okay, before coming to the drawbacks, so because this mechanism, it has several motion types, so it means this manipulator, this robot, is able to change from one motion to another motion. So this is the illustrations. We change from mode 1, Then we need to pass through what we call as a transition. Then it passes through the additional mode, and again it should go to the transition, and finally it comes to another motions. So we call this reconfiguration, and I'm working a lot on the reconfigurable manipulators. But the drawbacks from application point of view, the drawback of this mechanism, it has two links. So if we see the architecture of this robot, for one leg, it has two links, link 1 and link 2. So why it is a drawback for application point of view? If we have so many links, it means from dynamic point of view, we have more inertia that we have to deal with. So from control point of view, we have so many parts to control. So we change the architecture, what we call as a second generation. We change the architecture. Now we replace the first link to be the motors. So this is the fixed motors. All the vertical are the linear motors. And this is also a collaboration with our world-class professor last year, 2019. And the computations, the derivation of equations is actually almost the same as before. The behavior is a bit different and more interesting than before. We built this prototype. This is still under construction, and we didn't show the whole video because it's still in process, it's still in progress of publication. And what is the results for second generation of these mechanisms? Again, it has two types of four DOF. We used to call it 4 DOF, 4 degree of freedom motions. And the most interesting one is the additional 3 degree of freedom mode. How come one robot, it can have 4 degree of freedom, and at the same time, it can have another number of degree of freedom? This is also interesting challenge for us roboticians. We need to answer this. And after some identifications, we can come up with this mathematical formulations. And from these mathematical formulations, we can classify several dimensions, several shape of the platform. So it means if we change the shape of the platform, the motion will change also. So here is the video, the simple illustrations that I want to show you. Okay, so here is to show if we change the shape of the platform and the base, we have 4 classifications of the robot, and it is how are we going to change it, and this is how it looks. So we have several steps in executing the task. We usually draw it in CAD software first. After that, before building the prototype, we need to print it. We want to make sure that this robot is really able to perform our theoretical results. So, and yes, by 3D printed parts, we can show that the platform and the base changes. And we show it in, again, in CAD software, it has this motion. I will speed it up. Okay, and then we showed in our mockup. We call this as a mockup, the 3D printed part, and the prototype I have shown you was actually the last step for building the robot. So this is still the second step because the prototype is not done yet. So what I have shown you, what I'm showing you here is the mockup, the 3D printed. So this is what we call in robotics, we change into another motions. This is a big challenge for us, for roboticians, because for changing from one motion to another motion, we need to face singularity. So in the beginning, I have shown you what is singularity. For black hole, singularity means all the laws of physics, it doesn't apply. The same here in singularity, we need to find what kind of law that applies for tackling this singularity. So for crossing singularities, this is the ongoing project here in our lab. So we need to know first the workspace. The workspace again is the positions, the points in the space that we can reach by, that can be reached by the robot. The blue surface is the workspace of the robot. This is all symmetrical along the vertical lines, but the red one, the red surface is the singularity. So whenever the robot cross the singularity, the behaviors of the robot is uncontrollable. Even any kinds of law you want to apply, control, dynamics, kinematics, it does not apply. So this is very annoying. So we want to cross this singularity, but from dynamic point of view. So we generate a trajectory. So this trajectory, we built it two types of trajectory. The first trajectory, you can see these equations. The first trajectory is 5th degree polynomials, the usual one that you can find in many journals and papers. And the second is 8 degrees. And what happened in the force distributions of those two trajectory. So in the left picture, this is the force distributions. Here is what I'm going to interpret. What does this mean? So in the left picture, it shows that whenever this is the robot, when it moves, the robot moves with a very normal behaviors. And when it reaches singularity, it needs infinite value of forces. Millions of newtons of your motors, which is impossible to cross the singularity. So we manipulate from dynamic point of view. We derived algorithm from dynamic point of view. So at 0.8 seconds plus minus 0.8 seconds plus minus, we can cross the singularity from dynamic point of view. There are many aspects that we have to consider, but I'm not going to present all here. So this is the ongoing project that we want to apply this algorithm to the prototype. So in the mock-up is to show the kinematics, and in the prototype we want to show this algorithm, the dynamic algorithm. Okay. And next, parallel manipulators. I haven't done this anymore, but then this is still a collaboration with my colleagues in the lab. This is about ankle rehabilitation. We built these mechanisms, parallel manipulators for ankle rehabilitations. Actually, I intended not to continue, but there was an interesting counterpart with my partner. So we have a set of equations like this one. So by using or by computing these equations and formulating the Jacobians, matrices, so we can find what is the workspace, because of course, when we build the manipulators, we need to know whether this robot can perform this kind of motions, how big, if we put it in our leg, can the robot follow our motion and at which position? So we need to answer all of that by finding the workspace. So we can find the workspace. So here in the right picture, the gray surface is the workspace and the yellow is the point where the platform is singular. And as I mentioned before that I didn't continue that robot actually, but I had a counterpart with partner from Taiwan. So in mechanical engineering department, we have a collaboration in terms of academics. We have a double degree with the NCU. And then we started to do the collaborations in research. So our partner in Taiwan, he's developing a robot for surgery. So the surgery's name is femoral bone reduction surgery. From the name reduction, it doesn't mean that we want to reduce the bone. It's not. So if an accident occurred to someone, for example, he breaks his femur bone like this picture. So the doctors try to reduce the distance between those pieces of bones. So we call this reduction surgery. So far, what they did is they have to cut open the thigh of a human. So it will produce scars, it will produce more, it will take more time for recovery and so on. And why didn't we use parallel robot for surgery? So my partner is developing two kinds of robot that he wants to compare. Actually, these two robots, they are the same. Only that we switch the top part to be the bottom part. That's it. So those two robots are the same, but if we analyzed again, their behaviors are totally different. So how did we analyze this robot? We formulated the transformation matrix. We call it T1 and T2 because we didn't have name yet up to now. We call it robot 1 and robot 2. And we formulated the transformation matrix T1 for robot 1 and T2 for robot 2. From here, we can get velocity. Now, the way we formulated the velocity is a bit different than the ones we used to do. So the way we did now, we have to formulate the matrix. Why? Because this is new type of robots. This is hybrid robot because we combine two parallel robots together. So we need a new way to formulate the velocity properties to find the velocity of the robot. So this is an ongoing project. New results are coming up. Then the next one, this is at the end of my talk, about cable-driven parallel robot. From the name cable-driven, this is different than the parallel robots, but actually they are brothers and sisters. What is the difference is we replaced the rigid link. If we saw before, the robot uses many rigid links. So instead of using rigid links from dynamic point of view, we have to deal with the mass, the center of gravity, and so on. Now, how if we replace the rigid link with the cables? The cables is lighter, so that we can generate very high velocity and high acceleration. So actually, cable robots and parallel robots, they are brothers and sisters. So in cable robots, this is the prototype we built with collaboration with Polytechnic, the school next to ITS, Polytechnic Electronica. So we built this robot with 4 cables, and we have 4 pulleys here attached at the top of the robot. Now, how this robot works, we have a motors here. You can see we use the stepper motors. This is the first generation of the robot. We are building a second generation. So there are many drawbacks with this robot actually, because we are using stepper motors. There are too many vibrations here in the platform that we have to deal with. And we have a problem with the uncoiling cables. And what we did here, if we change the arrangement, whenever, this is also very trivial. So whenever if we build this robot, the first thing we did is we will attach the cable in each corresponding corner of this black box, right? Even if I want to build this robot, I will immediately attach the cable to the corner of each black box. But actually, this is also one major drawback. This contributes to the vibration as well to the robot. So how if we change the arrangement of the cable? How if, for example, I hope you can see this picture in the right picture. So how if we cross the cables? If we cross the cable, we add more constraints. So the robot will have less vibrations. So now the main contribution of vibration come from the stepper motor because it moves in step-by-step motion. Then, as I told you, now we are building the second generation of the robot. It's still under construction, but I will show you the concept of our robot. So this robot is for disaster rescue. The main motivation of this robot is in our country, you know, we are situated in the Pacific Ring of Fire. We faced many earthquakes and natural disaster. And how can we cope up with the aftermath of this accident? Usually we use cranes, but they are working independently. So how now if we collaborate those cranes together and they work together to lift up the debris, to lift up the victims and for recovery process. This is the ongoing project. We face problem as well when developing this robot. We faced what we call as a tipping rolling. So we see here in the left animation. For example, we put the payload to be 1500 kg and the robot is executing the task. Up at some point, one of the crane will collapse because it can be from the tension, it can be from the pose and etc. There are many mechanical aspects that we have to take in. And we introduced a concept of reconfigurable. So what is the concept of reconfigurable? So while the hook, the main point is executing a task, for example, for when lifting the debris, the arm of the cranes can also be extended, can also be shortened, and the angle can also be changed. So we can see here with the same payload, 1500 kg, the robot now doesn't collapse, the robot doesn't tip, the robot doesn't roll. All right, that's my talk. Thank you very much for your attention. Please, you may go to our website if you want to see more updates about our research. In our lab, we not only doing research in robots, we do also research in controls development for gyroscope with my colleagues. I'm not really doing it actually, but my colleague is doing development in controls for gyroscope and balance for vehicle. And if you want to see the updates or the video of the robots that I have just presented, you can also go to my channel in YouTube. I uploaded the video and animations of my robots. Thank you very much. And I'm open to any feedback, comments, and critics.
Okay. Thank you, Bu Latifah. Yeah, amazing this morning, yeah. From UAV till robot, and finally we have mathematics. I'm not disappointing to put Bu Latifah at the end of the presentation because Bu Enda actually is her teacher. You can imagine if I put it Bu Enda, Bu Latifah first, sorry, Mrs. Latifah first, then Bu Enda. It's not good. The attitude of mine.
I'm proud of her.
It's a really Indonesian way of talking. Okay, so it's very, very interesting, amazing, yeah. From UAV, and then we finally having a very mathematic. Bu Latifah should be in mathematics department like Pak Hendro actually. Because very close algebraic one. And we don't know actually the application somehow in some of my colleagues in mathematics. That's why the communication like this is really very important. Okay, I would like to see the chat room. Maybe Mr. Dr. Hendra having some question over there. And all participants, if you want to ask you can raise hand, or you can write it on the chat room, please. I mean, Mr. Hendro first, I think. Mr. Hendro, he is from Mr. Iqbal. Pak Hendro, actually, he is a doctoral student at Taiwan at this moment. He is a lecturer from Department of Mathematics.
Oh, great.
Maybe you can answer it here, and you can have discussion with Mr. Iqbal. Hello, Mr. Iqbal, are you in Taiwan? Yeah. Oh,
yeah.
I know your room now. Then you are in the office or in your room now? Still locked down, or it's already free from your home?
Yeah, already free, but currently I just ran Airbnb.
Oh, BNB.
Airbnb.
Okay. Maybe you can ask Mr. Hendro directly, Mr. Iqbal.
Actually, Professor Hendro already answered it. I just curious about how giving the knowledge in the first step for the robot, because currently I also doing a project with the kind of cobot with Intel US. So we did some machine tutoring method to give the robot with initial knowledge, so that the robot can learn by itself. Like maybe I give like a 5-step movement in 3 minutes, so that the robot can learn by itself for the next future. That's all. I just curious how Professor Hendro will give the initial knowledge for the cobots.
好，谢谢。先生，好久不见了。So speak a little bit Chinese.
I'm good.
Okay,
I'm good.
thank you for your curiosity and also interesting feedbacks for the cobots. It's just arrived yesterday actually, and since yesterday we also do some exercise to the robots, especially to kind of approach how to define how to move actually the robots by defining the pathways, the waypoints, and also we do exercise the robots, such as we hold the n effector of the serial manipulators, and we guide the robots to move the way, how to move the robots. So this kind of approach we are trying now to perform it, and our first step in observe this performance of robots actually is how accurate is actually the position that it might be achieved, and also how stable and how to identify actually the acceleration and deceleration between the acceleration and deceleration performance. So this actually already commercialized and established products developed by the industry. We actually would like to reverse to these robots to define our own next design criteria of our cobots by by our design. So probably we may. So you also might to to support, to supply the information of your research currently from Taiwan. So I think it's supposed to be a good way to synergize or to collaborate these two different approaches, similar collaborative robots in that way.
But we are focusing on the movement predictions for the robot, Professor Hendro.
I see. So the high level control for the predictive control command, actually.
Yes.
Okay. 好，加油啊！
So hard.
Prof Kim, do you understand the Chinese language, Prof Kim?
No, actually, I cannot understand the Chinese language, but Chinese character.
Oh,
I can read.
Okay. Okay. Any question? I've seen, I think from the participant, there isn't any question. Maybe you can have discussion. Actually, I want to ask Prof. Kim anyway. Maybe Prof. Hendra, if you want to ask something with Prof. Kim or Bu Enda or Bu Latifah. I mean, based on your experience, Prof. Kim, I want to ask first, yeah. It's amazing, yeah. We can have birth now flying in our room, yeah. and I still remember how difficult to develop, yeah. And as you mentioned that the birth fixed wing compared to what does it call, quadrotor, yeah, or like insect, yes, in the previous meeting.
Yes.
Which one actually more challenging in the future between insect or birds?
Oh yes, I think the insect one, the smaller, the size is smaller than the bird mimicking flyers. So still, and then the insect mimic one does not have the tail. So tailless flight is much more difficult because of the longitudinal stability. So
Okay.
still most of the guys all over the world are struggling from the problem without tail control. So tailless control is more difficult than the bird. Bird has tails. So that is very similar to the elevator on the fixed wing.
Okay. Yeah, we have one question actually for Prof. Kim from Dr. Astria and Irfansyah. He is from Department of Electrical Department. If you see on the chat, thank you for sharing the development of your burst mimicking. Anyway, Pak Irfansyah, could you please ask directly to Prof. Kim, please?
Okay, thank you very much, Dr. Sukhan. Professor Kim, good morning. Thank you for the presentation.
Nice to see you again.
Yeah, nice to see you again. I saw you mentioned about using Pixhawk Mini and the use of the Arduino Pilot environment for both the identification stage and also the control. My question is about the firmware that you use from Arduino Pilot. Is it Arduplane or Arducopter, or you have your own custom one?
Oh yeah. The simply Arduplane, because this aircraft is similar to the fixed wing type, so Arduplane is correct.
Oh, okay. Arduplane, and we were still new in this, so in our team we were only able to compile Arduino Pilot. We don't know where to start from which part of the Arduino Pilot source we can try our own control algorithm. And in my understanding, there are several options as well. Can you share just a bit about your experience?
So actually,
modifying Arduino Pilot?
We have two approaches. First one is we modify the Arduino Pilot source code directly, especially for the AC, the attitude control part. So we can modify the controller structure in the AC controller source code, and then secondly the mixing part, because we have different control surfaces, so we have to modify the mixing part code in the Arduino Pilot. So normally we are directly modifying the source code as such. And then another approach is nowadays we can utilize the Simulink. So we can design the controller and then mixing and then the fly mode selection by using the MATLAB Simulink environment, and then we can make that code can work with the Pixhawk.
Oh.
Yeah,
Okay.
with the
Is it available, the Simulink toolbox for?
Yes. So open mode, we can develop the but that environment should be with the PX4, not autopilot.
Okay. Okay. Thank you very much, Prof. Kim, for sharing this.
No problem.
Yeah. We'll try. We'll try.
Okay. Excellent. Yeah. Even though we are in the same university at a different place, and even though we have Prof. Kim from South Korea, we still have contact now. Yeah, we have discussed very nicely. Okay, we have a question from Pak Irfansyah still, yeah, to Dr. Latifah. Maybe you can mention it. You can talk with Dr. Latifah directly. Pak Irfansyah, please.
Okay, thank you very much, Dr. Subhan. Again, a very interesting talk, Dr. Latifah. I'm really interested in the way you also explain the singularities. It's some kind of locked position that we must avoid. So my question is actually from the electronic control system point of view. You showed us your parallel manipulator with many manipulators, and they have to work simultaneously together. When you already come up with the maths and know the control, the kinematics, the control, the kinematics, but when we try to implement the electronic control for all of them at the same time, it can be challenging, especially if it's high speed. Is there a need for a high speed parallel manipulator at the moment? I'm just curious because that might be really challenging.
Yeah, thank you for the questions, Pak Irfan. The use of parallel manipulators is really it depends on the applications. So for high-speed parallel manipulators, usually it is used in pick and place in the industry. So, you know, in industry, everything should be fast, everything should be precise, and so on. So using robots is one of, I'm not sure best, but it is one of the good solutions for doing that. And another application is, for example, I mean, the counter, on the contrary of the high speed is very low speed, for example, for surgery. So for surgery, it should be very slow and very precise. But for pick and place is, for example, in the end of the production line, a candy, for example, a packed candy, it should be placed in the box. So instead of using people, so we can use robots because it is precise, because you can control it. It can be pre-programmed before that. And it is very fast and very accurate. And yes, from control's point of view, before coming to control, we have to talk about the dynamics. The dynamics will be quite something, but of course we can solve it because already many analysis for solving that. And for controlling this, I believe, yes, it also depends on at which accelerations you want to reach. If you want it to be very high and at some point it should be stopped right away, then probably you have to consider not only acceleration, but also consider the jerk, the third derivative of time derivative of the position.
Yeah, and I really apologize for my ignorance. I did not realize until you mentioned it in your talk about the complexity of the dynamics. You mentioned 20 degrees of polynomials, really high degrees of polynomials. Just wondering how long does it typically take to design or know the dynamics of a system using just normal computers, for example?
Well, we just did the analysis dynamics for the robots with 4 legs. If you remember, I presented that. We just did the analysis for dynamics. If you do it numerically, I don't think it is difficult. Actually, there is also Adams to help the analysis. Adams software, ADAMS, Adams to analyze the dynamics. But we didn't use Adam because we want to propose an algorithm, so we need to know the derivation of the equation. So one way, if you solve it numerically, it doesn't take much time. It is normal. I mean, we can use MATLAB as well. But what we did try to do it symbolically. It took infinite time. So finally, we break in the middle. So one part is symbolic, one part is numerical.
Okay, so the reason why you want to do it symbolically is so that you can propose an algorithm, or why does it have to be done symbolically?
Yeah, I like everything to be symbolic because symbolic for me, from my point of view, for me it's like the brain. So if we change the dimension of the robot, we don't change the whole. The whole mathematical formulations. So also, for example, if we want to find the position of the robot, and if we change the dimension and everything, we are sure we don't lose something. But this is just from my experience, so please excuse me if I said something wrong. But from my experience, if I did it numerically, sometimes I lose something in this number because I didn't cover it. So now I like doing it symbolically.
Thank you very much. Thank you very much, Dr. Latifah. Dr. Supan. That's all from myself. Thank you.
Interesting, yeah. Very, very interesting, yeah.
Pak Subhan,
Okay.
sorry for interrupting. May I add some examples of implementation
Please.
parallel manipulators in high speed? So in our previous research study, we apply a steward platform. A steward platform is a kind of parallel manipulators, which is 6 actuators mounted on the base plates, and it moves the plates on the top of the steward platform, and it will be used to stabilize the gun or the weapon that we put on the steward platform to steady even the vehicle where is the steward platform and the gun mount on it. It moves radically, randomly, dynamically in every ways degree of freedom. So the question of Dr. Irfan related to the application of parallel manipulator in high speed is supposed to be still acceptable, reliable, and also feasible to be performed. So.
Okay. Okay. Thanks a lot, Mr. Hendro. Here is question for Dr. Enda from Mr. Diki, Mr. Math ITS. Pak Diki, can you ask directly to Dr. Enda, Pak Diki?
Yeah, thank you, Pak Subhan. So as I wrote in the chat, in Dr. Enda's presentation, she presented some mathematical models for predicting COVID-19 disease. Some of them are based on purely dynamical systems such as SIRD, and some others are a combination of mathematical models and also data, maybe by using machine learning or some other approaches. My question is the following. I would like to know from your experience which one is better and in what aspect they are better compared to the others. Thank you.
Thank you for the question, Pak Titi. May I ask you first? You mean comparing one model to other model or one method to other method?
comparing the purely dynamical model like SIRD, which is based on mathematical model, and also a hybrid model, combination of data and also mathematical model. Yeah.
Okay, thank you. Basically, it is classified as a data-driven model. So as long as we can provide very accurate data, then we can get very accurate also about the prediction. However, for the model of SIRD, we also can see that there are a lot of other model and also other more complicated model, and we use the simple model because of the availability of the data. So if the method, because we need additional method such as machine learning to obtain the accurate prediction of parameters. So as long as we can employ the method in excellent way, then we can get more accurate prediction. That's the point.
Okay, thank you.
Bu Enda, I would like to ask you a very simple question. Will be the Indonesian COVID decreasing, Bu Enda? Because as I know from the news that our Minister of Health is invited by the World Health Organization because he is successful to defeat the COVID. Is it only news or what is it? Pencitraan? What in English? I don't know.
Okay, I only can answer your question by stating Insya soon, Pak.
Okay. Yeah, it's look like it's challenging, yeah, because in Europe now it's second wave. I think in South Korea as well is second wave, Prof. Kim, yeah. But the thing is, in Indonesia, we are in the first wave, and that's why I think our Minister of Health got invitation from the WHO. It's amazing, actually. We are still on the first wave.
Yes,
hopefully
Not just first wave.
he said that it will cure by itself.
Okay. Okay, bye-bye. I think, Bu Latifah, can we have a picture for 5 moderator? And Bu Enda, please, still on your video. I would like to have a picture because most of the meeting I don't have picture for moderator and all speakers. I will, Prof. Kim, I would like to have a picture for a while, Prof. Kim, yeah. Just sorry. Just for a second only. Okay, thank you. Okay. Just a second. I make mistake, I think. Just a second. 1, 2, 3. Okay. Okay. For all speakers, Prof. Kim, Prof. Hendro, Dr. Latifah, and Dr. Enda, thanks a lot for joining us. And it's really very honored to have you with us, especially for Prof. Kim. Already we have 12 meeting. Bu Latifah,
Yes.
you have wood class professor last year is different with this year. We have 8 FGDs online and 4 workshops, and it's a very challenging. And finally, we have finished all the challenging program for this workshop for wood class professor program. I think again, there is no question. Yeah, again, thank you very much for joining us, for all participants. Hope you have to get some very interesting knowledge from all of speakers. I think this is not the end of our meeting or collaboration. I will have a follow up everything, especially for all of us here. We have Bu Latifah, which is very close with mathematics, actually. I will ask her to give a lecture in mathematics, especially for algebraic and analysis.
Okay, thank you.
Yeah. And Mr. Hendro is quite often supervising mathematics student. I think Bu Latifah should also supervising mathematics student to do some algebraic thing. And especially for Prof. Kim as well, we have join supervising for doctoral student, and we still have a commitment to do some supervising student. Anyway, again, thank you very much for Prof. Kim, Prof. Hendro, Dr. Latifah, Dr. Enda. Hope we have good health, yeah, and COVID will release from the world. Then we can traveling to South Korea. Yeah, Prof. Kim, yeah, and Prof. Kim as well can travel to Indonesia and meeting with Prof. Hendro, Dr. Latifah, and Dr. Enda in Indonesia, hopefully soon. Okay, I think I will close for our workshop, and I will contact you all after the meeting through the email or through the WhatsApp. Oke, Bapak Ibu semua, I would like to close in Indonesian, Prof. Kim, ya, sorry. Terima kasih Bapak Ibu semua. Pak Irfan, Mr. Irfan, who accompanying us, ya, helping us for successfully finishing our wood class professor program. This is the last meeting for 12 planning of our FGD and workshop. Oke, Bapak Ibu semua, thank you very much.
Thank you.
Hope to see you again soon, ya, in any other meeting. Okay, thank you very much, Bapak Ibu. See you. Assalamualaikum warahmatullahi wabarakatuh.
Salam warahmatullahi.
Thank you. Thank you. All of
Thank you,
your
Prof.
love
Kim.
and happiness.
Yeah.
Thank you.
Thank you.
Oke, Bapak Ibu.
Terima kasih Pak Irfan. Semoga sukses.
Yes, thank you, thank you.
Pak Irfan tetap sehat, tetap semangat.
Nah, sekarang bisa bahasa Indonesia.
Gak ada closing. Gak ada closing speak dari Profesor Kim, Pak Sufyan.
Apa?
Gak ada closing speak dari Pak.
Iya ya, sekadung lali.
Oh iya. Oh iya ya.
Lalet Pak Sufyan.
Ya, terima kasih Bapak Ibu semua. Saya kira tadi sangat apa ya? Gabungan yang sangat indah tadi ya. Ilmu-ilmu yang saya nggak nyangka tadi itu. Saya pernah dipresentasiin sama Bu Latifah. Karena persamaannya terlalu banyak dan panjang, komputernya itu sampai nggak cukup waktu itu presentasi di matematik. Aduh.
Bukan saya itu, Pak.
Iya, ya, tapi kan timnya.
Salah satu pembimbing saya ya.
Pak Yusti, Profesor siapa lagi? Manfred Yusti.
Ya, ya. Nah, ini tadi saya ngomong sama Bu Soleha. Bu Soleha bisa kerjakan itu, bidangnya aljabar masalahnya. Kali aja doktoralnya bisa di situ. Kan matematik sekali kan sebenarnya.
Iya.
Cuman orang matematik juga nggak ngerti kegunaannya, jadi nggak ada yang main-main ke sana.
Lu pernah tanya ke saya, Pak. Dan saya nggak tahu jawabnya gimana.
Ya, itu waktu pertama belajar itu, Bu Enda.
Iya.
Belajarnya.
Aku yang nggak tahu jawabannya.
Itulah hidup ya. Ternyata dekat gini juga nggak kenal ternyata ya. Jauh-jauh belajar kemana-mana yang dekat aja nggak kenal kalau nggak ketemu kayak gini. Ya Pak Hendra ya.
Siap. Ini masih streaming YouTube loh Pak.
Oh iya, ya tutup ya. Sorry. Nggak apa-apa lah.